Hello my dear students, welcome to video number 144 of my channel MALACHEMPHILIC, and this video number 144 is the episode number 83 of Chemical Thermodynamics, where the topic is thermochemistry. Already I am discussing thermochemistry and it is the 9th part of thermochemistry. So let's see what is there in the 9th part. So in the 9th part of this thermochemistry, I will discuss Born-Haber cycle. Now, what is Born-Haber cycle? You will find in a Born-Haber cyclic, it is a cyclic diagram and it involves the formation of 1 mole of ionic solid in the standard state. And it works on Hess's law. What is Hess's law? That is, enthalpy change of a reaction in the direct path will be same as that of if the reaction occurs through a number of steps. That means total enthalpy change in the number of steps will be same as that of the enthalpy change in the direct path. Okay, or enthalpy change is independent of the path followed. And in this cyclic diagram or cyclic path, you will find a number of steps, different steps like atomization, ionization, electron affinity, lattice enthalpy, etc. Okay, let's see one by one. Before going to actual Born-Haber cycle, first we'll discuss all these steps like what is atomization, what is ionization, then electron affinity, etc. See, first one, standard enthalpy of formation. Already you know these things, the standard enthalpy of formation. This is the enthalpy change when 1 mole of the compound is formed from its constituent element in the standard state. Standard state means that is 1 atmosphere pressure and 298 Kelvin, mostly 298 Kelvin temperature. Say here this metal and then, this metal and this halogen in the gaseous state, it is forming the MX solid. Okay. Now, next one is enthalpy change of atomization. What is that? That is the enthalpy change once again when 1 mole of the, here remember, 1 mole of gaseous atom is formed from the elements in the standard state. So 1 mole of the atom, that must be gaseous, formed from the elements in the standard state. Say for example, this halogen gas and here atomization, that means of dissociation of the XX bond, then 1 mole of this atom, gaseous atom is formed. And now this step is endothermic because you have to separate the atoms. They are bonded in the form of a molecule. You have to separate the atoms. Therefore, you have to supply energy. Next one is ionization energy. What is ionization energy? Ionization energy is, this is the enthalpy change once again when 1 mole of electron is removed from 1 mole of, once again, this gaseous atom or ions. So 1 mole is removed from 1 mole of gaseous atoms or ions. So this metal in the gaseous state, then say here I am taking one atom, one metal atom. So it is 1 electron is removed, so M plus metal ion gas. That means 1 mole gaseous ions will be formed. Okay. Now this will be endothermic. Why endothermic? Because you are removing in the atom, this nucleus is positive, electrons are negative. So electrostatic force of attraction is there between nucleus and electron. When you are removing the electron, that means you have to overcome that electrostatic force of attraction by the nucleus. So energy is required. So it is endothermic. And if multivalent cations are formed, say magnesium plus 2, aluminium plus 3, in that case, you have to consider first ionization energy, that is removal of one electron forming monovalent cation, then removal of second electron forming divalent cation, etc. And remember that this second ionization energy will be greater than first ionization energy, and third ionization energy will be greater than second ionization energy. Why? First ionization energy means the energy required to remove 1 mole of electron. Say from one atom, 1 electron is removed. Then that atom is already positively charged now. Then to remove another electron, already positively charged, so charge density is more. To remove another electron, more energy is required. So more ionization energy value for the second ionization. So successive ionization energy increases due to increased nuclear attraction. Now electron affinity. What is electron affinity? Here it is the enthalpy change when once again 1 mole of electron is added to 1 mole of gaseous atom to form 1 mole of this gaseous negative ion. Okay. So here you see. So here also this is important. This is 1 mole of gaseous negative ion should be formed. So this X from 1 mole of atom, the halogen atom, it takes 1 mole electrons. Then this ion, 1 mole of gaseous. This also will be gaseous. Okay. Now, see, this is exothermic. Why? Because you are adding electron. Already in the atom, nucleus is positive. When you are adding electron, then electrostatic force of attraction develops, so energy is released. Okay. But second electron affinity will be endothermic, because once the first electron is added, then it is already negatively charged. Then again, if you want to add 1 more electron, or if I tell that 1 mole of electron, then what will happen? It will experience the force of repulsion. Okay, you have to do it against the force of repulsion, so energy is required. So that's why it is endothermic. So for ions like O minus 2, O2 minus, both first and second electron affinities must be included. Now coming to the lattice enthalpy. What is lattice enthalpy? This is also the enthalpy change. See here. Here also, when 1 mole of the ionic solid, remember this is ionic solid, is formed from the gaseous ions. Ions will be gaseous, but 1 mole of the ionic solid will be formed. So M plus, metal plus gaseous, X minus anion gaseous, forming this ionic solid. Okay. In Born-Haber cycle, lattice enthalpy is exothermic. Why? Because this positively charged gaseous ion and negatively charged gaseous ion, they are coming together and forming the solid crystal lattice. That means electrostatic force of attraction is developing between the oppositely charged ions. So energy is released. Now coming to this Born-Haber cycle. Already I told you that Born-Haber cycle, it involves the formation of 1 mole of ionic solid. Okay, and it works on Hess's law, which tells that enthalpy change in the reaction is independent of path followed. And here are number of steps are there in the indirect path. And one step is this lattice energy. Already I explained what is lattice energy or lattice enthalpy. Okay. So this lattice energy cannot be calculated or measured directly. So with the help of Born-Haber cycle, in the indirect way, we can calculate this lattice energy, because this enthalpy of formation of this ionic solid from its elements can be measured. Other all these things, all these processes can be measured, but this lattice energy directly cannot be measured. So with the help of Born-Haber cycle, we can measure it. Okay. Now, as I already told you, it involves the formation of ionic solids, and it involves different steps. First steps, it is solid metal, and first step is the sublimation, because it has to convert it into gas, right? But here one mistake is there. So here this is not solid, this will be gas. Okay. Similarly, here also it will be gas. These two mistakes are there. Okay. So what are the steps? First step is the solid metal undergoes sublimation to form the gaseous metal. Okay. Then ionization. Okay, gaseous ions. Ionization already I have explained. So gaseous ion is formed from the gaseous metal. And here this is the non-metal, where first is undergoes atomization, forming the gaseous atom. Then electron affinity. Electron is added up, forming the gaseous ion. Now this gaseous cation, gaseous anion combine to form this ionic solid. These are gaseous, but the ionic solid crystal lattice is formed. So overall this energy change, that means this energy or enthalpy of sublimation, then enthalpy of ionization, then enthalpy of this atomization or dissociation, then enthalpy of electron affinity, then lattice enthalpy. This sum will be equal to this enthalpy of formation of this 1 mole of ionic crystal. Okay. Now, this cycle is built around the standard enthalpy of formation. So already I told you this point. This is standard enthalpy of formation of ionic solids. Okay, that means it provides the overall enthalpy change for forming 1 mole of these ionic solids in the standard state. Now, coming to this one problem based on Born-Haber cycle. This you try on your own. Then next class, I'll give you the solution. It is directly the application of Born-Haber cycle. But here you are not calculating, they are not asking you to calculate this lattice energy or this enthalpy of formation. They are asking the bond energy of this XX bond, this halogen bond, and it is given, all this information is given, that is here MX solid, that is ionic crystal, its dissociation energy is given. Ionic crystal is dissociating M plus cation in the gaseous form, X minus anion in the gaseous form. Lattice enthalpy, we get this reverse one. Okay, from M plus X minus this ionic solid is formed, but here they have given the value for this dissociation. Remaining are simple. This solid to gas, that means sublimation enthalpy they have given. Then this one, enthalpy of ionization is given. Then this bond energy you have to calculate. Okay, and then enthalpy of this electron affinity is also given. And this overall enthalpy of formation of 1 mole of solid is given. You have to calculate this one. So this will be your homework. So let's see whether you can solve it or not. Next class we'll discuss. Okay. Hope you have enjoyed. Thank you.